This is not science fiction. In the last 20 years, Earth has just been hit by the biggest solar storm ever recorded. Satellites shaken, power grids at risk, and the sky lighting up in ways scientists haven't seen in decades. What really happened? And should we be worried? Stay with me, because this solar storm could change everything. There are moments when everything looks stable, until it doesn't. And on January 2nd, the Sun presented that kind of illusion. Solar astronomers had been monitoring the surface closely, scanning for flares, filament eruptions, and anomalies in magnetic field lines. At first glance, the visible disk of our star looked relatively calm, but just below the surface, something was already shifting. The region of concern was called AR3219, a sprawling sunspot complex that had rotated into view days earlier. To the human eye, a sunspot is just a dark blemish, but in scientific terms it's a region of intense magnetic activity. These areas form when magnetic field lines twist and tangle beneath the solar surface, preventing heat from rising and cooling slightly compared to their surroundings. What looks dark is still thousands of degrees, but in solar terms, that's cold. AR3219 was large. At its widest, it stretched more than 15 Earths across. It was complex. Classified as a delta-class magnetic region, it meant opposite polarities were crammed into tight quarters. The kind of instability that almost always results in something explosive, but it was quiet for a while. Then came the twist. In the span of 2 hours on the afternoon of January 2nd, magnetic readings from the Solar Dynamics Observatory changed. Loops of magnetic flux connecting the poles of the sunspot began to writhe. The tangle reached a threshold. The field lines no longer held tension, they snapped. This is the moment when invisible processes turn visible. A bright flare erupted from the lower right quadrant of the sunspot. At first it looked like an ordinary M-class flare, strong but not extreme. But then the surrounding corona bulged outward. A massive arc of plasma, billions of tons of charged particles, began to rise from the surface. Instruments confirmed it almost immediately. This wasn't just a flare, it was a full halo coronal mass ejection. That phrase, full halo CME, means something very specific. It doesn't just describe a big explosion, it describes directionality. It means the ejected plasma is heading straight toward Earth, enveloping our field of view from orbit in every direction. It means the storm isn't going to glance by, it's going to hit. SOHO and Stereo spacecraft captured the event as it expanded. The corona, the outer atmosphere of the Sun, peeled back and exploded outward, forming a shockwave that accelerated particles ahead of it. Radio emissions spiked, X-rays flooded local space, and as the CME gathered speed, scientists began estimating arrival time. Usually it takes around 48 to 72 hours for such a mass to reach Earth. But something was different this time. Data from ESA's solar orbiter showed a rare feature in the interplanetary space ahead of the CME, a density gap, a region where solar wind had been swept aside by an earlier event, like a vacuum, like a corridor. This corridor acted like an accelerator. Instead of slowing, the CME retained its initial velocity, nearly 2,000 kilometers per second. At that speed, it would reach Earth not in 2 days, but in just over 30 hours. And when it did, it would do more than light up the sky. It would press against the edge of our world, and it would push. As the coronal mass ejection tore free from the Sun, scientists expected the usual slowdown. That expectation comes from experience. Most solar eruptions begin violently but lose momentum as they push through the constant stream of particles already flowing outward from the Sun. The solar wind acts like resistance. It spreads the storm out, dilutes its energy, and buys Earth time. This one did not slow. Within hours of launch, instruments aboard the Parker Solar Probe and Solar Orbiter began transmitting something unusual. The CME was maintaining speed. In some measurements, it was gaining it. That immediately raised concern because only a specific set of conditions allows a solar storm to do that. Ahead of the CME, the space between the Sun and Earth was not normal. 2 days earlier, a smaller solar eruption had cleared a path through the heliosphere, sweeping away much of the ambient plasma that normally fills interplanetary space. What remained was a region of unusually low particle density, a kind of wake left behind in the solar wind. The new CME entered that wake. Instead of ploughing through resistance, it moved through something closer to a vacuum. With little to slow it down, the shock front stayed tight and coherent. The magnetic structure did not fragment. The leading edge remained sharply defined. This mattered. A compact CME carries its magnetic field like a clenched fist. When such a structure reaches Earth, it delivers energy all at once instead of gradually. That difference determines whether a storm becomes a spectacle or a crisis. By the time the CME passed the orbit of Mercury, speed estimates had climbed beyond what models predicted. Analysts at space weather centers recalculated arrival times repeatedly, each update shortening the window. What initially looked like a 2-day warning compressed into less than 40 hours, and then something else became clear. The magnetic orientation of the CME was rotating. Magnetic fields inside a CME are not static. They twist as they propagate, but in this case, the rotation was trending southward relative to Earth's magnetic field. That direction is the most dangerous possible alignment. A southward magnetic field allows direct coupling with Earth's magnetosphere, opening pathways for solar energy to pour inside. This was not yet confirmed, but the indicators were troubling. Meanwhile, energetic particles accelerated ahead of the CME began arriving early. Satellites detected elevated proton flux long before the main shock. This phenomenon, known as a solar energetic particle event, can precede the storm itself and serves as an early warning that something powerful is on the way. Astronauts aboard the International Space Station were instructed to move into shielded sections as a precaution, not because impact was imminent, but because the radiation environment was already changing. On Earth, nothing seemed different. The sky looked the same. The sun rose and set normally, but above the atmosphere, invisible forces were rearranging the space our planet moves through. By late January 4th, the CME had crossed the halfway point between the Sun and Earth. Its shock front remained intact. Its internal magnetic field showed no signs of weakening, and the low-density corridor ahead of it persisted, allowing the storm to retain its destructive potential. At this point, scientists understood something important. This storm would not arrive gently. It would arrive all at once. And when it did, Earth's magnetic shield would have seconds, not minutes, to absorb the impact. The first contact would not be visible to the eye. It would be felt by instruments, by satellites, by systems built on assumptions of stability. The acceleration zone had done its work. The storm was coming faster than anything in 20 years. And Earth was directly in its path. It began as a ripple. The first detectable sign that the storm had reached Earth wasn't a flash in the sky or a surge on the ground. It was a soft compression, silent and invisible, recorded by satellites stationed hundreds of thousands of kilometers above us, floating near the boundary where our planet's protective magnetic shield meets interplanetary space. At exactly 0258 UTC, magnetometers aboard the GOES-18 satellite showed a sudden drop in magnetic field strength. Not a collapse, a shift. The kind that happens when an external pressure presses inward. That pressure had a source, and it had just arrived. Earth's magnetosphere, a bubble of charged particles and magnetic field lines that shields the planet from cosmic radiation, is not static. It flexes, breathes, and adjusts depending on solar activity. But what occurred on the morning of January 5th was not a gentle push. This was compression on a scale not seen in 2 decades. Over the course of just 7 minutes, the magnetopause, the outermost boundary of the magnetosphere, was forced inward by more than 6,000 kilometers. That may not sound like much, but to satellites in geosynchronous orbit, it meant they were no longer inside the shield. They were outside it, exposed. Those satellites began experiencing elevated radiation levels immediately. Engineers at ground stations noticed increases in single event upsets, glitches caused by particles flipping bits in memory registers. Most systems were built to handle these, but not at this volume, not all at once. Below, in the upper atmosphere, the consequences unfolded just as quickly. As the magnetic field was compressed, charged particles accelerated along newly aligned field lines. These particles, mostly electrons and protons, were funneled toward the poles. This happens in every solar storm. It's what creates auroras. But this time the energy was higher, the particle density thicker, and the velocity faster than expected. Within 15 minutes of impact, auroras were already forming, but this wasn't just an atmospheric show, it was a planetary interaction. High above the Arctic Circle, the Themis satellites captured the change in real time. Field lines that had been gently stretched behind Earth in the magnetotail snapped back like rubber bands, releasing stored energy. This process, known as magnetic reconnection, injected even more particles into near-Earth space. The system was cascading. And then came the chorus. Radio telescopes across the globe picked up broadband noise across the HF and VLF bands, a type of hiss that signaled turbulence in the plasma environment above Earth. This is not the kind of sound we can hear, but it marks the presence of rapid, chaotic movement in the ionized upper atmosphere, the kind that distorts radio signals and scrambles GPS. Earth was beginning to respond to the storm, and deep within that response was a signature. As the bow shock, the leading edge of Earth's magnetic defense, just bent under the pressure, a secondary wave formed behind it. This wave began to pulse, transferring energy into the radiation belts surrounding the planet. Satellites passing through these belts, already on edge from the first contact, began to detect spikes. These were not gradual, they were sudden, sharp, and patterned. This was the point when space weather experts knew something unusual had happened. Not just a strong storm, but a precise one. The CME had retained its structure across the entire span of space. Its magnetic field had not only survived the journey, it had arrived in an orientation that allowed maximum interaction. Earth wasn't just being brushed, it was being gripped. The magnetosphere was absorbing all it could, but the pressure wasn't easing. The real surge hadn't even begun. It started in the north. Over the tundra of northern Norway, where the night stretches long into January, fishermen and researchers looked up and saw the sky unravel. At first, it was just a flicker, a green haze low on the horizon. Then it rose, dancing in arcs. Vertical ribbons of light began climbing toward the zenith. They didn't just shimmer. They pulsed. At 0317 UTC, auroras were officially logged in the magnetic north zone. But what followed wasn't typical. The first hint that this was something different came from Tromsø's all-sky imager, a sensitive camera mounted near the Arctic Circle. It captured not just green bands, but intense crimson arcs above them. Red auroras are rare. They occur higher in the atmosphere, typically above 250 kilometers, and require enormous amounts of energy to form. When they appear, they signal a storm pushing far beyond routine levels. As the sky lit up in Norway, alerts went out. Minutes later, auroras were visible from parts of Scotland, Iceland, and even northern Germany. Witnesses described them not as subtle waves, but as full curtains, thick, brilliant, and fast-moving. Many expected them to fade within minutes. They didn't. Instead, the lights intensified. Over Alaska, where solar storms are no stranger, even seasoned observers were surprised. At 0343 UTC, magnetometers data from Fairbanks showed rapid oscillations. These ground-level fluctuations corresponded with overhead bursts of red and violet, colours normally invisible in auroras now breaking through due to extreme particle bombardment. But the most unexpected scene came from the south. In Tasmania, where auroras are usually rare and faint, the southern sky lit up in a full fan. Amateur photographers captured what looked like flames rising from the ocean, vertical plumes of light dancing above the southern horizon. Red, pink, even blue streaks appeared. Some were so bright they cast shadows on the ground. This wasn't just polar light. This was atmospheric ignition. The explanation lies in how the storm affected the ionosphere. When the solar particles collided with Earth's upper atmosphere, they didn't just dump energy at the poles. They spread further, reaching latitudes that rarely experience such bombardment. Charged electrons spiraled along Earth's magnetic field lines and collided with oxygen and nitrogen molecules in the thermosphere. These collisions excited the atoms, causing them to glow, but the energy levels were so high that even trace gases were activated. This is how we got the deep reds, from atomic oxygen glowing at extreme altitudes. But even more remarkable was the movement. Observers reported that the lights weren't just drifting or flowing, they were snapping, arcs that bent, split, and reformed in seconds. Some described it as the sky being stitched back together in real time. That motion isn't just visual, it's data. It reflects the rapid reconfiguration of Earth's magnetic field as it attempts to absorb and redistribute energy. This storm wasn't just bright, it was dynamic. Then came the skyward rays, narrow vertical beams of green and purple rising like fingers from the horizon. These were captured as far south as Nebraska and northern Utah. Places that might see one aurora per decade were now at the center of the show. Reports flooded in. Not from scientists, from drivers, from farmers, from people walking dogs at 4 a.m. who happened to look up and see something they'd never seen before. And then came the sound. In some areas, observers reported faint crackles and pops, not scientifically confirmed, but historically recorded during extreme auroras. Scientists remain cautious about acoustic claims. But in regions of intense magnetic fluctuation, there have been unconfirmed reports of static-like sounds near power lines and in quiet forests. Whether real or imagined, one thing was certain. The sky was alive, and it wasn't finished. While the sky above the poles was putting on a luminous display, inside the cockpits of commercial aircraft cruising at 39,000 feet, the mood was different. Pilots flying polar routes, the long-haul arcs between North America and Asia, began noticing small irregularities just after Ryu UTC. It started with a delay in high-frequency radio response. Normally, crews on these routes rely on HF communications to talk with air traffic controllers, especially when flying over the Arctic where line-of-sight VHF signals don't reach. HF uses the ionosphere to bounce signals over the horizon, and when the ionosphere is disturbed, those signals can vanish. And that's exactly what happened. Controllers at the Anchorage Air Route Traffic Control Center began receiving incomplete transmissions. Call signs were clipped, position reports were missed. Some flights had to repeat their transmissions multiple times just to confirm altitude and heading. It wasn't equipment failure, it was the sky itself that had gone silent. At 0413 UTC, the FAA's Space Weather Operations Center issued an HF blackout advisory for all routes above 80 Ktustd north latitude. The advisory warned of complete signal loss in the 3 to 30 MHz range, frequencies critical for both aviation and maritime communication. Without these bands, planes become isolated, unable to maintain routine contact with dispatchers or air traffic services. Flight AC-98, en route from Vancouver to Hong Kong, was among the first to divert. Unable to establish stable HF contact for over 30 minutes, the pilot opted to descend and reroute south over the Aleutian Islands. Several others followed. In total, more than a dozen polar flights were rerouted or delayed due to communication blackouts. Inside the cockpit, secondary systems were also beginning to react. Inertial navigation systems, which rely on precise timing, began to display slight drifts. Not enough to lose positional awareness, but enough to trigger crosschecks against onboard GPS. Pilots reported temporary discrepancies between what their flight management systems predicted and what satellite data confirmed. That's because GPS wasn't entirely stable either. As the upper atmosphere absorbed energy from the storm, layers of the ionosphere began to fluctuate in density. This caused GPS signals, which pass through the ionosphere, to bend, slow, or scatter. These subtle distortions didn't affect civilian smartphones much. But to aircraft relying on pinpoint accuracy for position, altitude, and trajectory, even small inconsistencies can matter. By 05 UTC, aircraft systems across multiple fleets were logging position variation alerts, automatic warnings that tell pilots to verify their coordinates through manual checks. In most cases, the discrepancies were minor. But in polar airspace, where navigational support is sparse and backup options are limited, even a few seconds of drift can add uncertainty. And uncertainty is something pilots are trained to avoid. As airlines rerouted traffic southward, coordination between control centers became critical. Over the North Atlantic, a corridor normally packed with long-haul traffic suddenly saw lower density. Meanwhile, routes over Siberia and the Central Arctic became congested as rerouted flights shared tighter lanes. This wasn't an emergency, but it was a stress test, and the system held. Crews communicated using SATCOM, satellite voice links, where available. Dispatchers and controllers adjusted flight levels, issued new tracks, and slowed departures to reduce overlap. Airlines burned extra fuel, passengers landed a few hours late, and thousands of travelers never knew that above the clouds, the invisible structure of their flight paths had been rewritten in real time by the sun. What most passengers saw was a glowing green sky out the window. What they didn't see were the silent protocols activating behind the scenes, the reroutes, the drift checks, the quiet confidence of systems designed for rare moments like this. And this storm wasn't finished testing them. Not all consequences of the storm unfolded in the sky. Some happened on the ground, quietly, through invisible layers of data that form the backbone of modern life. And the first sign came from systems that are rarely noticed, until they stop working as expected. It began with time. At 0512 UTC, network engineers overseeing high-precision trading infrastructure in Frankfurt began to notice a strange drift in atomic clock synchronizations. These clocks don't rely on wall time or local servers, they sync to GPS, and GPS, at that moment, was misaligned. This wasn't a full outage. The satellites were still in orbit, the signal was still broadcasting. But something had changed in how that signal behaved, and the reason was 300 kilometers above Earth's surface, in the ionosphere. Every GPS signal must pass through the ionosphere on its way to a receiver. Normally it bends slightly, slows down, then continues. These variations are modelled and corrected using sophisticated algorithms. But when the ionosphere is supercharged by a solar storm, those models fail. The charged layers fluctuate rapidly. One moment, they're dense. The next, they're nearly transparent. As a GPS signal passes through, it bends more than usual, or less. Sometimes it splits. This adds microseconds of delay. A billionth of a second error in a satellite's timecode can result in positional errors of several meters. That's exactly what happened. Agricultural equipment in Kansas, machines that rely on sub-meter GPS accuracy to till soil and plant crops, began logging path errors. Tractors that normally follow centimeter-accurate tracks began drifting out of rows. In vineyards, harvesters deviated enough to trigger onboard correction protocols. In Sweden, surveying teams paused work on infrastructure projects when their GNSS receivers reported sudden multipath errors, signs that GPS was bouncing unpredictably or arriving late. They weren't in danger, but the data could no longer be trusted. In Canada, precision drones used for land mapping struggled to hold station. Their GPS feedback loop kept correcting itself, hunting for a stable lock that never came. Flights were suspended. Even seismic sensors, which use GPS for position correction in tectonic monitoring, began showing jitter. The Earth wasn't shaking, but to the instruments, the surface looked like it was pulsing ever so slightly. The illusion was caused by fluctuating satellite delay. Then came the maritime warnings. Cargo vessels transiting the North Atlantic reported GPS inconsistencies while crossing mid-ocean waypoints. Their onboard navigation systems flagged positional deviation alerts, warnings that their projected location didn't match reality. Some ships shifted to backup inertial navigation until signal stabilized. The global ripple continued. In India, telecom synchronization systems experienced brief errors as GPS-based time servers lost precision. These servers keep cell towers and data centers operating in sync. When they fall out of alignment, voice calls drop, data packets stutter, and handoffs between towers become unreliable. None of these events made headlines, but they were recorded, logged, and investigated, and at the center of each was the same invisible culprit: a hyperactive ionosphere, pulsing with energy injected by the sun, bending and twisting the very structure of space through which all GPS signals pass. It wasn't just position that was being distorted, it was time itself. And when the foundation of global synchronization drifts, even by microseconds, the ripple moves outward, touching planes, ports, banks, grids, and everything else built on the assumption that satellites will always say exactly where we are and when. During this storm, that assumption broke, and the world had to adjust, in silence. Far from the satellites, aircraft, and auroras, something else began to stir. Deep within the infrastructure we use every day, hidden inside the long metallic veins of the modern world. At 0604 UTC, a minor voltage fluctuation was logged at a power substation near Rovaniemi, Finland. Just a few seconds later, a transformer at another substation farther north briefly tripped offline and reclosed. It wasn't catastrophic. No alarms went off in the city, but operators noticed it. A flicker, a surge, and then stability. By itself, this kind of event wouldn't mean much. But when similar anomalies started appearing in Sweden, Norway, parts of northern Canada, and even the upper Midwest of the United States. All within the same 20-minute window, the pattern became undeniable. This wasn't equipment failure. It was geomagnetism coming from below. When a powerful solar storm compresses Earth's magnetosphere, it doesn't just affect the skies. It also changes the magnetic field at ground level. Those changes, rapid and wide-reaching, induce electric currents in the ground itself. These are called geomagnetically induced currents, or GICs, and they have a preferred path, metal. Long conductors like power lines, pipelines, and railway tracks act like antennas for these currents. As the Earth's magnetic field fluctuates, it generates voltage along these conductive paths. The longer the line, the more vulnerable it becomes. This is what happened during the storm. As the compressed magnetic field wobbled and reconfigured, electric fields were generated over large areas of ground. In Scandinavia, where bedrock conductivity is high, the effect was amplified. Current flowed into high-voltage transmission lines, transformers, and substations. The result? Small surges, voltage regulation issues, unexpected harmonics on the grid. Most of these were absorbed and corrected by modern systems, but not all. In one district in Lapland, a voltage regulator on a rural distribution network failed to compensate fast enough. For 37 seconds, voltage levels spiked above safe operating thresholds. Streetlights blinked. A few appliances tripped their safety breakers. In Canada's Northwest Territories, operators saw reactive power levels spike along a 500 kilovolt line. That spike lasted just under a minute, long enough for the grid's control software to reroute power flow preemptively. No blackouts, but it was close, and these were not isolated events. Back in 1989, a solar storm knocked out the entire Quebec power grid in less than 2 minutes. Since then, utilities have hardened systems, added sensors, and created protocols. But storms like this test all of it, silently. And then came the trains. In Sweden, the national rail operator began reporting signal anomalies in their control systems. Not from satellite drift or software bugs, from electrical interference. Metal rails, stretching for hundreds of kilometers, were acting as unintentional receivers of geomagnetic current. In one instance, an automatic train protection system misread a signal, briefly placing a section of track in occupied status. No train was there, the fault was cleared in seconds, but if left uncorrected it could have halted service on that line for hours. Even underground systems were affected. In Helsinki's metro network, a magnetic anomaly caused a brief disruption in a tunnel communication loop. Trains continued safely, but operators had to reset a localized signaling node manually. None of this made the evening news. No one lost power for long, no injuries, no disasters. But beneath the surface, the storm was threading itself through wires, iron, copper, and steel, touching systems that millions depend on without ever realizing it. The flicker on the ground wasn't just a warning, it was proof. The sun had reached through the sky and into the earth. The storm wasn't finished. While the skies glowed and the ground hummed, an older instrument began to falter, one that humans have trusted for over 1,000 years. The magnetic compass. It started subtly. In northern Canada, field researchers logging GPS coordinates noticed something odd, a mismatch between what their devices were telling them and what their physical compasses indicated. The shift wasn't massive, just a few degrees at first, but it was enough to raise questions. Magnetic north was no longer where it used to be. The explanation lies in the invisible geometry of Earth's magnetic field. Normally the field lines arc gently from one magnetic pole to the other, not fixed points, but drifting zones anchored by molten iron movements deep inside Earth's core. This field is what compass needles align with. But when a solar storm strikes, it distorts that field, sometimes dramatically. The result is a temporary reshaping of magnetic lines across entire continents. At a geomagnetic observatory in Tromsø, Norway, magnetometers recorded a sudden deflection in horizontal intensity, a sharp kink in what should have been a smooth, stable trace. Just under 110 nanoteslas of deviation. Not enough to throw off a jetliner, but enough to mislead anyone relying on analog navigation tools. Fishermen in Arctic waters noticed it too, boats drifting off course, netlines dragging west instead of north. One seasoned captain told a local paper, The needle lied to me for the first time in 20 years. Aviation authorities were watching closely. Because in the upper atmosphere, aircraft rely on a blend of GPS, inertial systems, and magnetic headings. During strong solar storms, magnetic deviation can confuse cockpit instruments, especially for smaller regional planes without multi-redundant systems. Airports in high-latitude zones like Anchorage and Reykjavik activated their space weather protocols. Flight paths were adjusted, polar routes were rechecked, and magnetic runway headings, the numbers painted on the tarmac that tell pilots which way they're pointing, were being monitored for rapid shifts. But the bigger impact wasn't in aviation or fishing, it was in wildlife. Migratory species, birds, turtles, whales, are known to use Earth's magnetic field as part of their internal GPS. When the field shifts suddenly, their navigation maps blur. Birds may veer off course. Whales might beach themselves in unfamiliar coves. Sea turtles, freshly hatched, can end up swimming the wrong direction entirely. Around Hudson Bay, a wildlife tracker monitoring snow geese reported erratic patterns. Flocks that should have been heading south appeared to circle wide, then double back before realigning. Was it wind, predator avoidance, or had the storm nudged the lines they followed? At a research facility in Germany, scientists watching a colony of lab pigeons, all tagged with magnetic sensors, saw them briefly lose directional cohesion during simulated solar activity. The birds hesitated, flapped, then regrouped. Something had changed. It wasn't permanent. Magnetic fields recover, lines stabilize. But during those intense hours, Earth's compass was scrambled. And this raised an even deeper question. If solar storms can twist our magnetic field so easily, and if our species, our machines, even our animals still rely on those invisible lines, what happens when the next storm is 10 times stronger? We've seen records from 1859 when the Carrington event ignited telegraph poles and lit the sky red over the Caribbean. If something like that struck today, the compass wouldn't just skew, it could collapse, and in that moment, no satellite, plane, boat or bird would be flying straight. For now, the needle has settled, but it remembers. So do we. It began with a delay, not an explosion, not a blackout, just a moment of nothing. At 08:52 UTC, GPS receivers across Alaska, Greenland, and parts of Scandinavia began to report irregularities. For most civilians, nothing felt wrong. Their phones still showed their position on the map. Navigation apps loaded. But behind the interface, subtle cracks had opened. Each GPS signal is a whisper, a timing pulse from a satellite orbiting over 20,000 kilometers above Earth. These pulses are incredibly faint, relying on precise atomic clocks and clear space between the transmitter and receiver. The ionosphere, Earth's outer shell of charged particles, acts like a lens, bending, slowing, and sometimes scattering these signals as they pass through. During a solar storm, that lens becomes a shattered mirror. At Stanford's GPS laboratory, scientists were watching in real time as the total electron content, TEC, of the ionosphere surged. Normally, GPS signals pass through a stable field of electrons, but now, as solar particles slammed into Earth's upper atmosphere, the electron density spiked to chaotic levels. That surge doesn't destroy the signal, it distorts it. Picture this. 2 identical GPS signals sent from 2 satellites meant to arrive in perfect sync, but one is delayed, not by seconds but microseconds. That delay, multiplied across systems, turns into positional error. For a phone, that might mean your location bouncing between 2 streets, but for agriculture, aviation, or military systems, it's much more serious. In precision farming, tractors guided by GPS veered off course, cutting crooked lines through fields that were supposed to be perfectly straight. In mining operations in Chile and Australia, automated rigs paused mid-operation, unable to verify their coordinates. Some switched to backup inertial systems, others simply shut down. But it was in aviation where the silence became most dangerous. Onboard commercial aircraft, GPS isn't just for maps. It's used for approach guidance, altitude corrections, and terrain avoidance, especially in remote or mountainous areas. During the storm's peak, pilots over Greenland reported GPS dropouts. Their systems showed momentary freezes, backup navigation took over, and no planes were lost. But the message was clear. Space had disrupted the ground again. Even timing networks, the invisible scaffolding of our digital world, weren't immune. Because GPS doesn't just tell us where we are, it tells us when we are. Banks use GPS timing to sync transactions across continents. Stock markets rely on it to timestamp trades. Power grids need it to synchronize load sharing between cities, and telecom networks depend on it to hand off calls between towers seamlessly. When the timing pulse drifts, even by fractions of a second, the ripple spreads fast. At a data center in Finland, a timing server flagged a phase lock loss error, a minor glitch, quickly corrected. But multiply that error across hundreds of systems and things begin to desynchronize. Packet loss increases, buffers fill, networks slow. And then came something stranger. In the United States, an amateur radio operator scanning GPS L1 and L2 bands reported an eerie phenomenon, a blanking, not interference, not noise, just gaps, periods of dead air where signals should be. He called it ghost quiet, as if the satellites were still transmitting, but something was intercepting, absorbing, or misrouting them. No agency confirmed that. But the possibility remains, because when a magnetic storm twists the ionosphere and bends the global signal lattice, anything, or anyone, listening in might not just hear the disruption, they might exploit it. For now, the silence has passed. GPS has stabilized. Timing pulses are once again syncing the machines of Earth, but for a brief window, the sky stopped speaking, and we learned how much we depend on the whisper. It started with earthworms. In the early hours of January 3rd, farmers across rural Norway, Russia, and Canada began reporting something strange. Patches of soil were steaming, not from frost but from heat. Earthworms were emerging en masse, writhing just beneath the surface. In Finland, a herder found his metal fence buzzing faintly, not with wind, with current. The ground somehow was alive. Solar storms are best known for their light, the auroras, the sky's green and violet curtains. But their most dangerous effects are often hidden, beneath the surface, in the quiet flow of electrical currents through the Earth's crust. These are called geomagnetically induced currents, or GICs, and this storm produced some of the strongest GICs ever recorded. When solar particles slam into Earth's magnetosphere, they distort the planet's magnetic field. That distortion sets off electric currents, not just in the sky, but deep underground. Rock layers act like resistors and capacitors. Long conductive structures, like power lines, pipelines, and railways, become unintended antennas, and the planet itself becomes part of the circuit. By mid-morning, grid operators in Sweden issued a Level 2 GIC alert. Transformers began to heat, not just from load, but from DC currents forcing their way backward through systems built for alternating current. Some substations automatically shut down. Others throttled voltage to avoid a surge. In Quebec, Canada, home to one of the most sensitive grids to GIC, control rooms lit up with warnings. Engineers rerouted power, reduced transfers between provinces, and manually disabled sensitive circuits. But while cities stayed online, rural monitoring posts told another story. Soil probes at various depths showed microcurrents pulsing through clay-rich earth. In some fields, aluminum irrigation systems buzzed faintly. Farmers with implanted pacemakers reported momentary heart irregularities when standing near exposed rebar or wet furrows. At one wind farm in Denmark, grounding rods glowed faintly in the dark. It was not fire. It was something else. Earth returning energy to the sky. At the European Geosciences Union, scientists examined real-time data from magnetotelluric stations, buried sensors that measure electric fields beneath the crust. What they saw shocked them. Long, slow, undulating waves of current, spanning hundreds of kilometers, rolling eastward beneath northern Europe. The source? The solar storm above. The shape. Unlike anything they'd modelled before, some currents bent, rebounded off buried mineral seams or amplified near fault lines. These weren't random discharges. They followed structure, geometry. In Finland, near a decommissioned copper mine, the underground sensors formed a pattern, pulsing in triangular synchrony every 90 seconds. One geophysicist called it a magnetic heartbeat. And yet there was something else. A mystery even more grounded. In Alaska, near Fairbanks, ground-penetrating radar used by a university field team recorded a bright echo at shallow depth. At first they thought it was permafrost melt, but repeated scans showed movement. The object, roughly the size of a van, had shifted position by several centimetres during the storm's peak, not vertically, but sideways. As if something metallic beneath the soil had conducted current and moved. No known vehicle or equipment matched its location. They marked the coordinates. The team returned the next day. The echo was gone. Whether it had sunk, dispersed, or been buried again remains unknown. But the magnetic fingerprint left behind, a sharp, localized spike, did not match any natural formation. Across the globe, as the storm faded, Earth exhaled, currents weakened, transformers cooled, fences stopped humming, but the soil remembers. Electricity flowed through it not as chaos, but in rhythm, aligned with cosmic winds and planetary scars. We often look to the sky for signs, but sometimes the message is written beneath our feet. The warning didn't come from Earth, it came from the satellites. Orbiting silently above us, tens of thousands of machines. From small CubeSats to massive weather observatories, these artificial eyes are designed to track, map, and listen. But on the morning of January 3rd, several began behaving strangely. Not all at once, not dramatically. Just off. One by one, satellites in medium Earth orbit reported anomalies, minor attitude corrections that didn't fully resolve, gyroscopes registering rotational drift, magnetometers showing unexpected alignments. For ground controllers, these weren't critical failures. They were subtler, almost like a cosmic nudge. Then the tilts began. The GOES weather satellites, part of the US National Oceanic and Atmospheric Administration's space weather system, are some of the most resilient platforms in orbit. Their job is to look outward, toward the Sun, and monitor incoming particle flux. But GOES 17's onboard systems detected a yaw shift, only by a few degrees, but enough to skew its imaging. Engineers assumed a minor thruster misfire, until GOES 16, on the opposite side of the Earth, reported the same issue, same magnitude, same time. The ESA's Sentinel satellites, responsible for Earth observation, followed suit. Subtle shifts in orbit orientation forced teams to suspend imaging for 37 minutes. Those images, when examined later, contained blurred light trails, not from camera shake, but from the entire frame rotating mid-capture. And in low Earth orbit, SpaceX's Starlink constellation had a moment of silence. For 4 minutes, over 200 units lost their orientation lock. Most reacquired their signals autonomously, but a handful, less than 10, remained in safe mode for hours. When queried, onboard logs showed a simultaneous spike in magnetometer deviation and solar panel inefficiency. That shouldn't happen, not together, and certainly not across satellites in different altitudes. Space weather analysts rushed to find a cause. The solar storm, still intense as it brushed the upper magnetosphere, was already triggering ionospheric fluctuations. GPS signals were slowed and refracted. But these new disturbances weren't from above. They seemed lateral, tangential, as if a sideways ripple had passed through the orbital lanes. Researchers turned to swarm data, clusters of satellites designed to fly in formation. ESA's Swarm A and Swarm B reported coordinated torque corrections. The problem wasn't their internal hardware, it was external. The magnetic field they used for orientation had warped, not weakened, warped. For the first time, Earth's magnetic envelope had bent just enough to make satellites momentarily forget where down was. Imagine being on a ship in calm waters and the compass needle begins to slowly rotate. Not because the ship is turning, but because the ocean itself has changed. That's what the satellites experienced. But the most telling moment came from a satellite that wasn't even online. LGEOS 2, a passive laser-ranging satellite launched in 1992, has no power. It simply reflects laser pulses from Earth, allowing scientists to track tectonic shifts with millimeter precision. During the storm's peak, its reflected pulses returned 0.8 milliseconds early. That means one of two things. Either the satellite shifted in its orbital path by nearly a kilometer, or space-time around it compressed temporarily. Neither answer is comforting. The possibility that space itself flexed, even by microscopic degrees, under the influence of electromagnetic pressure, suggests that what happened wasn't merely atmospheric, it was structural, invisible scaffolding, what physicists call the magnetospheric current sheet, had been pushed, bent, or disturbed in a way not previously modelled. NASA's Heliophysics division initiated a data freeze. All logs from magnetosphere monitoring satellites were secured, quietly, without public announcement, and then silence. The satellites stabilized, orientations resumed, Earth's orbital lanes returned to their geometric calm, but the anomaly left a fingerprint, a tilt, not just in machines but in the confidence of those who guide them. Because when our most precise instruments wobble, it means something deeper has shifted. Deep inside Antarctica's Concordia station, where temperatures regularly plunge below -90 degrees Fahrenheit, some of the world's most sensitive astronomical instruments operate in pristine silence. Seismometers, cryogenic infrared telescopes, magnetic flux detectors. They're designed to function where nothing else can, isolated from city lights, radio signals, and even magnetic interference from nearby metals. These devices don't flinch at storms. They've survived over a decade of solar maximums, but on January 3rd, they froze, not from cold, from confusion. It started with a small drop in telemetry. At 0324 UTC, the Magnetic Observatory at Dome C, usually stable to within nanoteslas, recorded a null zone, not a spike, not a fluctuation, just flatline. For nearly 2 minutes, the Earth's magnetic field, as sensed at that point, appeared to vanish. Software flagged it as sensor error. But 3 nearby stations, Vostok, Amundsen Scott, and South Pole Traverse, showed the same thing. It wasn't a glitch, it was a pause. Meanwhile, in northern Canada, the SuperDARN radar arrays reported something stranger. The sky went quiet. These radar systems bounce high-frequency signals off the ionosphere to study auroral currents and polar wind patterns. Their antennas are always in motion, scanning sectors and measuring particle movement in real time. But at that same moment, sort of 324 UTC, the scans returned nothing. Not a weak return. No return. The signal vanished as if the upper atmosphere no longer existed. Less than 90 seconds later, the entire array rebooted. Power levels hadn't dipped. No software updates were running. Yet diagnostic logs showed full system halt. Engineers couldn't explain it. The last line of the internal report was chilling in its simplicity. No medium detected. In Chile's Atacama Desert, 2 hemispheres away, the ALMA telescope facility, an array of radio telescopes listening to deep space, experienced a hard lock on several of its dishes. Operators described it as if the arms of the telescopes refused to move. They didn't jam, they didn't fail mechanically, they just ignored commands. The dishes had locked onto a specific sector of space near the ecliptic. That wouldn't be strange, except that the target wasn't one of their scheduled observations. No known celestial object was in that direction at the time. It was almost as if something local within the solar system had pulled their focus. For 3 minutes, the system refused manual override, and when it finally released, the internal logs showed a burst of broadband interference that matched nothing on record. No Earth-based signal, no solar flare. It wasn't noise, it was structured. Spectrograms showed repeating peaks spaced at mathematically perfect intervals, suggesting either a highly artificial source or a natural resonance not yet catalogued. Whatever it was, it forced ALMA's mainframe to dump and reset its memory cache. And during this moment, across multiple instruments worldwide, the same thing occurred. They froze, not from failure, but from indecision. High-speed cameras atop Mauna Kea missed 5 seconds of star tracking, despite having redundant image buffers. LIGO, the Gravitational Wave Observatory, flagged a microsecond event that didn't match any expected merger pattern. And in Japan, the Kagura Neutrino Observatory recorded a sudden spike in background noise, followed by silence, like every listening post in the world had taken a breath and held it. What these instruments all shared was precision, machines that operate without rest, without error for years, and yet during this window of time between 0324 and 0327 UTC, something stopped them from observing reality as it was. Not broken, not blind, just still. And if that doesn't frighten scientists, it should. Because when instruments designed to measure the universe suddenly refuse to see it, the question becomes, what was so incomprehensible that even our machines looked away? In classical astronomy, orbital paths are geometry in motion: ellipses, arcs, parabolas. Every known object from asteroids to planets traces curves dictated by mass and gravity. These paths can be predicted with uncanny accuracy, centuries into the future or thousands of years into the past. Geometry in this context is not optional. It is law. But on January 3rd, one object didn't obey. That morning, the European Space Agency's Solar and Heliospheric Observatory, SOHO, transmitted a set of tracking coordinates to its ground team in Darmstadt, Germany. They were routine updates, logged every 12 minutes. The team was monitoring 3I Atlas as it moved past the Earth-Jupiter corridor. But what they noticed in this particular transmission broke more than protocol. It broke the curve. At 0612 UTC, 3I Atlas appeared precisely where expected, cruising on a slingshot arc that used Jupiter's gravity to pull it forward. But by 0624 UTC, the next predicted position was off by 7 arc seconds. That's a tiny number, barely a smudge in the telescope's lens. But the anomaly wasn't in the size of the deviation, it was in its shape. Instead of a gentle gravitational bend, the new path showed a compound curve. 2 bends stacked atop each other, with the second curve diverging upward, against momentum. That shouldn't be possible. NASA's JPL team reviewed the orbital telemetry and reran the model. Same result. The curve had been broken and replaced with a form of motion that had no clear precedent. It wasn't circular, it wasn't parabolic. It was like the object had hit an invisible boundary, skimmed it, then pivoted around it. That's when geometry stopped being a tool and started becoming a mystery. When they layered the path over previous solar system trajectories, one startling overlap emerged. The arc of the new curve, when plotted in 3D, mirrored the orbital resonance patterns observed in certain Trojan asteroids, objects that remain trapped in gravitational nodes created by Jupiter and the Sun. These Lagrangian points, L4 and L5, are stable zones. They don't move, they don't bend. But the new curve didn't just mimic that pattern. It mimicked a shifted version of it, as if there was a second, invisible gravity well operating just outside the traditional map, pulling 3I Atlas into a new alignment. Even more bizarre, when the shape of the curve was modelled using a polar coordinate system, the path generated a mathematical structure known as a litius spiral. This spiral shape doesn't naturally occur in planetary motion. It's found in electromagnetic resonance fields, in plasmas, in antenna radiation lobes, in artificial signal patterns. Some scientists refused to even accept the data. They assumed it was a glitch in interpolation, an error in how 2 points were connected. But when SOHO's independent backup confirmed the same geometry, the conversation shifted. What kind of object alters its trajectory in a form that matches signal physics more than space mechanics? Could it be interacting with something unseen, a magnetic contour, or a structured field? Or was it producing the field itself? That's when an astronomer from the University of Bern noticed something chilling. When overlaying the path of the broken geometry onto an old Voyager 1 plot from 1980, the curves nearly aligned, not in direction, but in curvature ratio. The math was eerily close. Voyager 1 had passed through a region of anomalous magnetic noise near Saturn in June of that year, and now, over 40 years later, 3I Atlas was tracing a shape that echoed the same invisible map. It's as if the object wasn't drifting, it was navigating. And in that moment, geometry stopped being prediction and became communication. If that curve was a message, then its shape might be a code. And the fact that every gravitational model failed to explain it suggests something even more unnerving. That we may no longer be in charge of defining the rules of motion within our own solar system. Something else might be drawing the map now. It started with a flicker, not a burst, not a flare, just a flicker, barely above background noise. But it wasn't coming from the Sun, and it wasn't coming from Earth. The signal was logged at 4:19 UTC by a polar-based observatory in northern Finland, part of a lesser-known radio telescope array designed to monitor auroral events. The system had picked up a brief collimated radio pulse, concentrated, narrowband, and unusually directed. At first, the technicians assumed it was just spillover from solar wind interactions with the magnetosphere, but then they looked at the angle. The pulse wasn't angled downward into Earth's upper atmosphere as natural auroral signatures are. It was angled upward, outbound, travelling away from the Earth-Moon system and tracing straight back to 3I Atlas. By the time this data was cross-referenced with LOFAR, the low-frequency array spread across Europe. It was already escalating. LOFAR confirmed a second beam just minutes after the first, this time at a slightly different frequency, but again, narrowband, directional and originating from the exact coordinates of 3I Atlas's core. Now the term beam has weight. In natural astrophysics, we observe beams in phenomena like pulsars, those ultra-dense neutron stars that spin and emit radio waves in lighthouse-like pulses. We also see them in active galactic nuclei and quasars, but comets, interstellar debris, never. There is no known process, chemical, thermal, electrical or magnetic, that causes a comet to emit a tight collimated beam of coherent radio energy. Outgassing creates chaotic jets, fragmentation causes scatter. But this wasn't chaos, it was intentional direction. Worse, the beam was traced across 3 different frequencies, all falling within the hydrogen line spectrum, the 21 centimeter wavelength that is commonly monitored in deep space communication efforts. It's the same band the SETI Institute monitors for potential intelligence signals, because hydrogen is the most abundant element in the universe. If you wanted to announce yourself to the galaxy, this would be the channel. Scientists scrambled to make sense of it. Could it have been a reflection? A natural echo? A solar flare bouncing off dust? But no local event matched. No solar activity had occurred in that moment. No auroral spikes. No satellite interference. No nearby Earth-based cores. The beam wasn't bouncing off something, it was being sent. And then came the final confirmation, one that turned the scientific confusion into outright disbelief. The signals showed modulation. Within the pulse train were microfluctuations, tiny dips and peaks in intensity and frequency that repeated at irregular but statistically significant intervals. This is not how natural radiation behaves. It's how encoded transmissions behave. A team at Caltech ran a preliminary modulation analysis and found that the pattern bore resemblance to a chirped signal, a signal in which frequency increases or decreases over time. In radar and communication systems, chirped signals are used to improve range detection and reduce noise. It's a design principle. That meant one thing: design. 3I Atlas wasn't just emitting energy, it was possibly communicating, but to what and to whom? Some theorists quickly tied this to a broader hypothesis, one that had floated in fringe astrophysics for decades, that objects like 3I Atlas might not be ships or machines in the traditional sense, but autonomous nodes, beacons, relays, navigational points in a larger system-spanning network, each one activating when triggered by proximity, gravity, or electromagnetic thresholds. And here, just days after passing Earth's orbital shell, one such node had seemingly beamed outward. Not toward Earth, not toward the Sun, but toward Jupiter, as if something was waiting there, or worse, listening. Now that the beam was on record, there was no turning back. Every deep space antenna on the planet had been retuned. Every hour, more anomalies emerged. But the question now wasn't about origin, it was about intent. Because in all of known physics, such a beam should not exist. And yet, there it was. There's a difference between drifting and deviating. One is passive, the other carries intent. After 3I Atlas passed Earth, most agencies expected a relatively clean trajectory toward the outer planets. The models were stable, the projections were straightforward. But then came the wobble, subtle, almost dismissible, but growing with every hour. It was JPL that first saw the anomaly. Using data stitched from NASA's Deep Space Network, they noticed that 3I Atlas wasn't holding a constant vector. It was drifting, not in a straight line, but in a rhythmic, almost oscillating pattern. Think of it like this. If a typical comet is a marble rolling down a hill following the slope, 3I Atlas began moving like a marble that suddenly develops a heartbeat, pausing, shifting, and adjusting in ways that defied Newtonian expectations. And here's where things got serious. Each of these oscillations, or wobbles, occurred at predictable time intervals, not random, not chaotic, but regular. Engineers mapped it across 5 key metrics: velocity, orientation, tail alignment, plasma sheath width, and angular spin. The shifts were real, and they formed a wave. Now imagine that, an interstellar object pulsing through space with what appears to be internal corrections. The wobble wasn't due to gravitational perturbations from known planets. It wasn't from solar wind variability. It didn't match any previously catalogued orbital interference. Instead, it looked self-initiated. What if the object was adjusting itself, not to avoid debris, not to escape gravity, but to realign its position, perhaps for communication, perhaps for synchronization, or perhaps for something even more unthinkable: orbital insertion? Because as the data kept coming in, scientists realized something even stranger. The wobble wasn't random in space, it was relative to Jupiter. Each minor deviation realigned 3I Atlas's heading, closer toward a new set of coordinates, ones that, curiously, weren't perfectly aligned with Jupiter's center of mass. Instead, they hovered around a narrow band of orbital altitude known as the Lagrange corridor, a zone of gravitational equilibrium where small objects can remain stable without much energy input. That's not coincidence. That's navigation. Spacecraft use Lagrange points to save fuel. Artificial probes exploit them to hover near planets without burning through propulsion. But comets, they don't wobble into gravitational sweet spots by accident. That's when attention shifted back to the strange signal from the previous chapter, the directed beam. If that pulse had indeed been sent toward Jupiter, and now the wobble was aligning 3I Atlas with a stable orbital corridor, then this wasn't just an object on a journey, it was approaching something. Some astronomers proposed a provocative theory, that 3I Atlas wasn't aiming for Jupiter at all, but rather a location near Jupiter, possibly one of the planet's moons, or a stable point along its magnetic equator, where previous anomalies had been detected. Others pushed it further. They noted that the frequency of the wobble, its timing and intensity, matched harmonic multiples of Jupiter's radio emission bands, especially those associated with the Moonio. That raised an alarming possibility. Was the object tuning itself, aligning not just spatially but resonantly, like a musical instrument syncing to a cosmic frequency? And if so, what happens when the tuning completes? The orbital wobble wasn't a malfunction. It wasn't caused by a collision. It wasn't a dusttail acting as drag. It was coordinated, a maneuver, a dance, and the implications were immense. Because if 3I Atlas could perform controlled orbital corrections without visible thrusters, then we are no longer looking at a passive traveller. We're watching something capable of positioning itself with high precision in complex gravitational environments, and it's doing so in our solar system. The final shift in trajectory was scheduled to take place in less than 48 hours, and when it did, scientists feared it would bring 3I Atlas into one of the most stable and most strategically important positions any object has ever held around Jupiter, a perfect place to wait. Jupiter has many moons, but one stands apart. Io isn't just another celestial body, it's a furnace, the most volcanically active object in the solar system. Its surface is constantly reshaping itself, its atmosphere pulsing with sulfur and plasma. But what makes Io even more unique is what it does to Jupiter's magnetosphere, and someone, or something, may be paying attention. In the hours after the orbital wobble became undeniable, scientists began triangulating the likely endpoint of 3I Atlas's altered path. The answer was astonishing, a near alignment with Io's orbit, not a collision course, not a flyby, but a sync. This is where things became deeply unsettling. Io doesn't just orbit Jupiter, it charges it. As the Moon moves through Jupiter's magnetic field, it creates an electrical current, called the Io flux tube, that extends all the way into Jupiter's poles. This is a current of staggering scale, generating auroras, plasma waves, and field-aligned discharges that ripple across the gas giant. It's like Io is an electric plug, and Jupiter is the outlet. So why would 3I Atlas steer itself toward that? Telescopes on Earth and in orbit began tracking what they called the event cone, the anticipated window where 3I Atlas would intersect the electromagnetic corridor trailing Io's motion. That path wasn't gravitationally stable, it was unstable, volatile, and constantly shifting, due to the immense plasma interactions between the Moon and Jupiter's magnetic field. But it was predictable. And that's the detail that cracked everything open. On January 3rd, scientists at the Max Planck Institute mapped the curve of 3I Atlas's trajectory and found it matched a known resonance band, one associated with Io's orbital harmonic oscillations. That meant the object wasn't just heading near Io, it was targeting a specific harmonic window, timed to intersect with a plasma burst that occurs only once every 12 days. This wasn't timing, it was synchronization. To get this precise, you need internal timing systems, you need trajectory control, you need to know what you're aiming for, and you need to have a reason to aim for it. But what would that reason be? Several theories began circulating inside classified astronomy forums. One pointed to the magnetic reconnection events that occur during Io's alignment with Jupiter's magnetic axis. During these bursts, enormous amounts of energy are discharged, creating corridors of low-density plasma that extend outward, brief tunnels of minimal interference, capable of transmitting signals or even passing through undetected. In other words, a channel. Another theory suggested 3I Atlas might be using Io's electromagnetic interactions not for transmission, but for scanning. By moving through the field at a specific phase of its distortion, the object could gather information on how energy behaves near massive gravitational and magnetic interactions. It would be like moving a sensor through a lightning storm, not to avoid it, but to measure the patterns. The third and most radical theory was quietly passed around between European Space Agency engineers. They noticed a timing pattern between 3I Atlas's internal pulses, recorded from its beam emissions, and the rotational speed of Io. Each pulse lined up not with Earth, but with Io's spin. Why? Because Io is tidally locked. One side always faces Jupiter, and from that side, any emissions, whether magnetic, plasma-based or energetic, would be redirected straight toward the gas giant's upper ionosphere. If 3I Atlas was listening, this would be the perfect vantage point. If it was responding, it would be the shortest pathway, and if it was doing both, then something intelligent was occurring inside that alignment. Right now, 3I Atlas is only hours away from that corridor. Its signal has grown faint, but the orientation of its tail has subtly shifted, facing backward, not toward the sun, but toward Io. It is watching, it is moving with purpose, and soon it will enter the most electrically charged environment known in the solar system. We've never seen an interstellar object do this, and we don't know what it will do next. There's a region around Jupiter that doesn't behave like anything else in the solar system. It's called the plasmasphere, a torus-shaped cloud of ionized gas trapped within the planet's magnetic grip. It's formed primarily by Io's volcanic emissions, which spew out sulfur and oxygen atoms that quickly become electrically charged and caught in Jupiter's field. Over time, this plasma coalesces into a ring, glowing faintly in the ultraviolet, moving in sync with the planet's spin. Until now, that spin had been stable. Until now, the plasmasphere had been symmetrical. That changed the moment 3I Atlas entered Jupiter's outer magnetodisk. On the morning of January 4th, data from the Hisaki satellite, a Japanese ultraviolet space observatory, showed a kink forming in the torus. Not a drift, not a wobble. A sudden compression in one quadrant of the ring, directly opposite from Io's position. This compression was accompanied by a drop in energy density, as if something had either siphoned plasma from the region or deflected it. The first thought was a magnetic anomaly. The second thought was 3I Atlas. At first, the connection seemed speculative. The object was still thousands of kilometers away from Io's orbital line, and no probe had ever recorded an interstellar body disrupting a planetary plasmasphere before. But within hours, every plasma monitoring station, both on Earth and in orbit, picked up something else, a phase shift. Jupiter's plasma ring has a pulse. It rotates once every 10 hours, driven by the gas giant's own spin. That pulse emits a detectable signal in the radio band. But suddenly that rhythm broke, not entirely, but subtly. Every few minutes, there was a gap, a momentary delay in the rotational echo of the plasma torus, as if something was dragging on it, slowing it, or feeding from it. And when researchers overlaid the coordinates of these phase delays with the projected trajectory of 3I Atlas, they matched perfectly. The disruption points followed the same curved path the object was taking as it skimmed the magnetic boundary layer, just outside the densest plasma, but close enough to interact. The question changed from did it cause this to what is it doing with the energy? Here's where things get stranger. Radio telescopes in Chile and Australia tuned to the decametric band, frequencies associated with planetary emissions, began receiving short bursts of low-frequency radio waves. These bursts didn't come from Jupiter's poles. They didn't match any known pattern from the planet's auroras or lightning. They were triangulated to the region near the disrupted plasmasphere, and embedded in those bursts were gaps, timed intervals that didn't match natural static, gaps that looked more like on-off sequences. Early signal analysts compared it to a binary pattern, not data per se, but a rudimentary modulation, like a lighthouse blinking at regular intervals. Was it a byproduct of interaction? Was it a form of feedback? Or was it a transmission? One theory proposed a magnetoplasma coupling mechanism, where 3I Atlas was using the natural field energy to power or amplify its internal systems. Another proposed a resonance cascade. The object was tapping into Jupiter's spin-locked plasma rhythm to generate motion or recalibrate its path. But the most debated hypothesis came from a lone physicist at the University of Oslo. She proposed that 3I Atlas was mapping the plasma torus not just for navigation, but for replication. Because a torus isn't just a shape, it's a magnetic containment field. And if 3I Atlas was carrying internal energy, heat, particles, or something more exotic, it might be seeking to store it in a new shape, a new field, one that could carry energy across interstellar distances. That would mean the plasmasphere wasn't being disrupted accidentally. It was being learned from, mimicked, rewritten. And in the middle of this invisible chaos, 3I Atlas just kept moving, silent, slow, and aligned with a layer of the solar system no probe had ever mapped at this depth before. Something is happening in Jupiter's electromagnetic skin, and we may be watching the blueprint of something ancient awaken. It began as a flicker, barely visible, barely measurable, but not for long. Just past midnight UTC, the MAVEN spacecraft orbiting Mars detected an unexpected spike in ultraviolet radiation. At first, it was dismissed as a background flare, possibly solar, possibly instrument error. But then Juno's ultraviolet spectrograph positioned near Jupiter picked up the same signature, not from the Sun, from the side of Jupiter. And more specifically from the exact corridor where 3I Atlas had just passed. What MAVEN and Juno detected was no ordinary burst. It wasn't a steady stream like solar wind. It wasn't scattered like auroral discharge. It was a focused, fast-rising, short-lived pulse of ultraviolet light, lasting only a few seconds, but carrying with it a signature spectrum that didn't match anything currently observed in Jupiter's magnetosphere. Scientists dubbed it an ultraviolet shockwave, and it raised immediate alarms. Let's break down why this was so strange. First, ultraviolet emissions from Jupiter are typically tied to its auroras, generated by charged particles spiraling along magnetic field lines at the poles. But this pulse didn't come from the poles. It originated near the magnetic equator, a region that should be quieter, more stable, less prone to sudden energy releases. Second, the shock wave had a frequency tilt. That means the intensity curve was not symmetrical. It ramped up fast, peaked in a narrow band, then decayed exponentially, leaving behind a residual signature that lingered across several wavelengths. Some compared it to a chirp, like a sonar pulse in deep ocean. But most telling of all was the trajectory. Earth-based telescopes picked up a secondary scatter of the burst, reflected faintly off Jupiter's upper clouds and the icy surface of Ganymede. By calculating delay times between the reflected light, scientists triangulated the source of the shockwave to within a few hundred kilometers. It was exactly where 3I Atlas had made its closest tangent. The event triggered a rapid-fire alert to deep space monitoring systems. Instruments that hadn't been pointed at Jupiter were suddenly redirected. The Hubble Space Telescope, currently observing a distant nebula, was quietly repositioned to verify the anomaly. And then something even more unexpected happened. A mirror pulse, smaller, dimmer but structurally identical, was detected near Europa, a full 6 minutes later. There is no known mechanism by which Jupiter's magnetosphere should echo an ultraviolet emission across its moons with such precision. The speed and propagation suggested directionality, as if the pulse was not random but part of a pattern, or worse, a mechanism. What could cause that? One possibility: a magnetic shock front. Similar to how coronal mass ejections can cause shockwaves in the solar wind, the interaction between 3I Atlas and Jupiter's plasma belt may have created a kind of localized detonation, a magnetic ripple that superheated particles and caused them to emit UV radiation. Another possibility: energy extraction. The theory goes like this. 3I Atlas, during its brief skim past Jupiter's magnetic equator, tapped into the field using a mechanism not unlike a transformer coil, pulling energy, storing charge, and releasing the waste heat as a burst of ultraviolet light. But then came a third, far stranger idea. What if the burst was not waste, but signal? A beacon to something else? Because the mirror pulse near Europa carried the same modulation, same tilt, same decay rate, as if the system wasn't just being used, but coordinated. A few researchers floated the term resonant handshake, a communication method that uses celestial magnetic fields as the medium, not the message. The UV burst, in that view, wasn't a byproduct. It was the event, a call or a response, one that travelled through fields, not wires, and just as quickly as it arrived, the shockwave vanished. No second pulse, no audible aftermath. But one final trace remained, an unexpected ultraviolet shadow, drifting slowly across the edge of Jupiter's limb, like a fog that had forgotten to dissipate. And 3I Atlas, still silent, still moving. But something around it had changed, and the next probe to notice was Voyager 1. Voyager 1 was never meant to return home. It was built to leave, quietly, permanently, slipping past the edges of the known solar system with a golden record and a one-way mission: observe, transmit, and fade into interstellar darkness. But on January 3rd, something changed. The Deep Space Network station in Canberra received a transmission packet from Voyager 1 that contained a subtle anomaly, not in the data itself, but in the orientation metadata. The probe had adjusted its attitude control. That may sound routine. Occasionally, Voyager 1 performs tiny thruster burns to keep its antenna aligned with Earth. These corrections are pre-programmed or triggered by onboard sensors reacting to drift. But this wasn't one of those. This change was unscheduled, unprompted, manual, but not from Earth. The change was small, just under 0.04 degrees in pitch. But for a spacecraft over 15 billion miles away, that angle matters. At that scale, it's equivalent to shifting your gaze from one galaxy to another. And here's the part that set every control room on edge. The new orientation aligned perfectly with the coordinates where 3I Atlas had just exited the Jovian system. Let that sink in. Voyager 1, floating beyond the heliopause, beyond the reach of our planets, our sun, our magnetic field, tilted its gaze back inward toward a piece of cosmic debris it was never designed to track. And it did so without command. Engineers at NASA's Jet Propulsion Laboratory pored over telemetry logs. Could solar wind pressure have nudged the spacecraft? Unlikely. Could sensor error have caused false drift correction? Possible, but no other metric showed error thresholds being crossed. One theory began to surface. Voyager had responded to an external signal. This would not be unprecedented in science fiction, but in real-world terms it's nearly impossible. Voyager's systems are not equipped to receive complex transmissions from unknown sources. Its sensors are limited, its memory is minimal, its logic paths are fixed. But what if the trigger wasn't complex? What if it was simple? Binary. Some researchers proposed a model. An intense burst of directional energy, such as the ultraviolet shockwave recently observed near Jupiter, could, at just the right frequency, induce a sensor spike even at interstellar distances. Imagine a tightly focused laser of ultraviolet light with just enough residual power to trip an aging spacecraft's gyroscope sensor. By design, it's a stretch. But then again, so is everything about 3I Atlas. More curiously, the new orientation didn't just point toward the general vicinity of the comet's trajectory. It aligned with a calculated future coordinate, a point where 3I Atlas would intersect the heliopause boundary in exactly 42 days, assuming it maintained its current acceleration curve. And that raised the question, how would Voyager 1 know where to look? Because this wasn't just a turn toward a light in the sky, it was a calculated gaze,